In this video, we continue our study of the second derivative. We are going to show that when the map f is C2 smooth, then the second derivative is actually going to be symmetric. Let me state the proposition that is going to form the central part of this video. Proposition: let f from u to C2, u to f be a C2 smooth map. C2 smooth map. Let E1, E2 em be the standard basis of f, which is just the Euclidean space Rm. So take the standard basis for Rm. Then for A in U, we have an explicit expression for the second derivative. Remember, the second derivative acts on a vector v. This will produce a linear map from E to F, and it acts on another vector w also coming from E, and the net output of that is a vector in F. And remember, E1 to Em is a basis for F, so we are going to write down an explicit formula for this vector d2fav acting on W in terms of the standard basis for Rm. And that expression is somewhat convoluted, but we will unpack this right after we finish stating the proposition. This is d of the gradient of F1 at the point A acting on V, this whole thing dot product W, and this thing is the component of E1, okay, plus dot 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 plus the final term will be d the gradient of Fm at the point A acting on V, this dot product with W Em, okay, and this is true for all V comma W in E. It's a very convoluted expression or formula for the d2favw for the second derivative. Here this dot is the standard inner product, So this is this somewhat complicated looking expression for the second derivative, and the final part of the theorem is furthermore d2f is a symmetric map, that is d2fa acting on V and that whole thing acting on W is the same as d2fa acting on W, the whole thing acting on V. So there are two parts to this proposition. The first part gives an explicit expression for the second derivative, assuming the function is C2 smooth, of course. Then the second part says that this d2f is a symmetric map, which just means that if you act V and then act W, it's the same as acting W and then acting V. So let's unpack this convoluted expression. Okay, let me rewrite the expression here so that it's still there in front of our eyes. So this is d of gradient of F1 at the point A acting on V, this dot product W E1 plus dot dot dot, the same thing d of gradient of Fm at A acting on V dot product W Em. So this is the expression we have. Now first of all, note that gradient of Fi is a map from U to Rn, right? So it takes as input a point of the set U and its output is a vector in Rn, okay? So it makes perfect sense to talk about the derivative of this map, because this is starting from an open subset of an Euclidean space and landing up in an Euclidean space. Okay, so it makes perfect sense to take the derivatives of these fi's, of the gradient of fi's. Okay, so this expression d of gradient of f1 of a is nothing but treating the gradient as a map from u to r and then taking the derivative. So this map d grad fi would be a map from u to, sorry, it will not be a map from u, it will be a map from Rn to Rn. That is E to E. Remember, E was always Rn. Okay. So this d gradient of fi is a linear map from Rn to Rn. Rather, I should specify this, what I have written is not wholly accurate. This is at the point A is a map from Rn to Rn, linear. Okay, and now this acts on a vector v, that is this vector here, to produce a vector in Rn. So this entire thing will output a vector in Rn, which we take the dot product. So let me write the dot product in a more prominent way here also. Okay, so you can take the dot product with w, which will give a scalar. Thankfully, because I am putting a vector in front of it, there is an e1 here. Okay, so now I hope it's clear what is it that this proposition is asserting. Somewhat convoluted, but it needs to be done to show the symmetry of the second derivative. Okay, so the proof is going to be straightforward. Even though the statement looks complicated, we will just plow along straightforward lines and we will get the proof. Of course, we are going to write f as f1 to fm. Write f as f1 to fm. We know from an earlier proposition, we already know that dfx acting on a vector w is, in terms of the basis e1 to em, it's nothing but df1x w e1 plus dot 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 dfmx w em. So this we proved this earlier when we talked about the Jacobian matrix and all that. Somewhere around that time I had stated what the derivative is going to be in coordinates. So this is an expression for dfx w in terms of coordinates. Recall f1 is the component function, so it's a map from u to r. So df1 would be a linear functional. So df1x w will indeed give you a real number. So this entire expression does make sense. Okay, so second thing I want to note down is that this was unsaid in the statement of the proposition, but I cannot leave it unsaid in the proof. Gradient of fi, which is a function from u to Rn, is differentiable. And why this is differentiable? Because the function f is C2 smooth. So I'm going to leave it to you to verify the details. Why is this function differentiable? So each gradient fi is actually differentiable. This is important because otherwise this complicated expression on the right hand side doesn't even make sense. If the function's gradient of fi's are not differentiable. Okay, so the C2 smoothness will immediately give that gradient of fi is differentiable. Now, what is it that we have to do? We have to compute the second derivative. For that, we have to take a difference of this type, dfa plus v minus dfa. Okay, so we have to take an expression of this type. Now, this is going to be an element of LEF, this difference, because both dfa plus v and dfa are linear mappings from E to F. Okay, in fact, if w is in the vector space E, then this dfa plus v minus dfa acting on w is given by what I had said earlier. This is just nothing but d of f1a plus v minus d of f1a this whole thing acting on W, and this thing is the component of E1, plus 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 dot 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 an analogous expression EM. I'm not going to bore you by repeating the same thing again and again. So this just follows from this. So we have an expression for the difference dfa plus v minus dfa acting on a vector w. So this acting on a vector w is really not going to matter much, as you will see in the later part of the proof. Okay, now what we are going to do is subtract the claimed expression for d2f. So we have this complicated expression in the statement for d2fa v w, which is this complicated thing. I'm going to subtract that to this, okay, and I'm going to group the terms together in terms of the coordinate standard basis E1 to EM, and let's just consider the first term, and the same analysis will hold for the rest of the terms. So subtract the claimed expression for d2f and consider just the first term. Consider the first term that is corresponding to E1. Okay, this is nothing but this term d f1 a plus v minus d f1 a, this whole thing acting on w minus d gradient of f1 v dot product w, and this whole thing E1. Okay, now here is the part which is interesting. What I'm going to do is I'm going to rewrite this expression, because what follows involves taking the derivative of the gradient. It's natural to shift this entire thing, in fact including the w. It's natural to try to expand that in terms of the gradient. So we can rewrite this as gradient f1 a plus v minus gradient f1a, the whole thing dot product w minus d of gradient of f1 v dot product w. Okay, this is starting to look really nice. Of course I must write down the E1 term. Okay, this is starting to look exceptionally good, because we can write this as gradient of f1 of a plus v minus gradient of f1a minus d gradient of f1 acting on v, the whole thing dot product w, and the whole thing is the component or coefficient or coordinate corresponding to E1. Excellent. Now this is nothing but E of v dot product w E1. Okay, this is just E of v dot product w E1. What is E of v? Where E is the sublinear function coming from the definition of differentiability of gradient of f1. Remember, right at the beginning of the proof I made the remark that gradient of f1 is in fact differentiable. So there is a linear map and blah 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 blah, there is an error function blah 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 blah, all that. I'm just calling that error function, that comes error term, as E of v. Okay, so what is the net upshot of all this? The net upshot of all this is that the first term's Euclidean norm is less than or equal to norm of E of v norm W product. This is just the Cauchy-Schwarz inequality. I've just used the Cauchy-Schwarz inequality here. Okay. So and this term divided by norm V goes to 0 as V goes to 0 because E is sublinear. Okay. So from this I'm going to leave the trivial details to you. It follows that f is twice differentiable with the claimed derivative. So this concludes the proof of the first part, modulo some detail which I have cleverly left for you. Okay, now we have to show symmetry. That's the final part of this proposition. Well, observe that D of gradient of F1 is a real symmetric matrix. And I leave it to you to ponder why this is so. This is again because F is C2. This D of gradient of F1 is going to be a real symmetric matrix. Okay. So let's just look at again the first term. If I show that if you interchange V and W in the very first term, it's not going to make a difference, then it's not going to make a difference in all the other terms also with the same analogous argument. So the first term is going to be D of gradient of F1 of A acting on V dot product W. Okay. So this first term and the second term are both vectors in Rn. I'm representing them as column vectors. So to write down the dot product, I can also treat it in matrix notation, and I can just write this as D of gradient of F1 of A acting on V. This will produce a column vector. I take the transpose and make it into a row vector and then multiply by W. Okay. So of course here I have made this identification, this left hand side, top hand side is actually a number, whereas this expression, since I'm treating it as matrices, I'm treating both W and this vector as matrices, this is actually a 1 cross 1 matrix, but it's harmless to identify a 1 cross 1 matrix with the corresponding entry. Okay. Now what I'm going to do is I'm going to take the transpose of this whole thing, which is going to give the same value because it's a 1 cross 1 matrix, and the transpose as you can see is nothing but V transpose. I'm taking the transpose and writing equality. V transpose D of gradient of F1 okay, this is not really taking the transpose, this is just using the formula for transpose of a product. I am treating everything. V here is going to be a column matrix, D this is a square matrix, so this is going to be just V transpose D of gradient F1A transpose, but that's itself, because I just said that D of gradient of F1 is a real symmetric matrix, and here we have W. Okay, I have just taken the transpose. Okay, now it is now at this point that I want to take another transpose. I want to take a transpose of this, okay, which is going to be itself, because we are dealing with 1 cross 1 matrices. When you take the transpose, you get W transpose D of gradient of F1 at the point A acting on V. Okay, and this is same as D of gradient of f1 at a w dot product v as claimed. So each of the coefficients corresponding to E1 to EM would be symmetric. If you interchange V and W, nothing's going to change. Therefore, this whole D2 FA is symmetric and the proof is complete. Okay. So this proof will not be used in the rest of the course, but it is good to know it's a bit abstract and a bit complicated because a lot of things have gotten compressed with the abstract language, but once you unwind everything and unpack everything, it's not that difficult. So one final definition and exercise. So definition, this will make the second derivative somewhat more palatable and concrete. Let f from u to r be C2 smooth. Be C2 smooth. Okay. We define the Hessian HF of A to be by definition just the matrix of partial derivatives. Okay. So I should probably write Hessian of f at A to be this. So this matrix is in fact a symmetric because second partial derivatives are assumed to be continuous. We have in the C2 smooth setting, so second partial derivatives, the mixed partial derivatives are equal. So this matrix is going to be a real symmetric matrix. So the exercise for you, which will let you come and get your hands dirty on a concrete version of what has happened in this video, let f from u to r be C2 smooth, then show that HFA is D2F at A in a natural way. So relate this concrete matrix of second partial derivatives with the abstract D2F, the bilinear map or the map that takes values in LEF. It takes a vector E and maps it to a vector in LEF. Relate both of them and see that they are both related in a natural way. So in the analogous way, you can talk about higher order derivatives. There will be mappings from E to a very, very complicated space. Alternatively, you can also view them as multilinear mappings. Essentially, there is no greater difficulty in the idea. It's just notation becomes somewhat unwieldy. So I will not pursue this any further. I have given references to several prominent textbooks that deal with this. So I will conclude with just this second derivative part and the Hessian matrix. So this concludes our exploration of the second derivative. This is a course on real analysis and you have just watched the video on the symmetry of the second derivative.